Okay, guys, so this is one of your homework problems. This is the 2011 free response number 2. And you watched a video previously that we did on a table problem, so we kind of consider this a table problem. Since it's number 2, it is calculator active, but we'll kind of talk about even on calculator active that there's some spots that you might want to stop on so you don't lose the point that you would have earned. I mean, even if it's calculator active, once it's all numbers, it's a full credit answer. So Mr. Herney drew my table up there for me. So we have our time in minutes, and we have the time frames 0, 2, 5, 9, and 10. And then we have our values for h of t, and h of t is representing degrees Celsius. And those outputs are 66, 60, 52, 44, and 43. So temperatures in degrees Celsius. So the stem of our problem says, as a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for 0 is less than or equal to t, which is less than or equal to 10. And I haven't talked about this much, but when you read that something is differentiable, if you are differentiable, that automatically implies that you're continuous. So sometimes when I read that, I'll just write it down, even if I don't end up using it ever. If we have h of t, which is differentiable on the closed interval from 0 to 10, this notation means that implies that you are also continuous on the closed interval from 0 to 10. So if I ever had to use something where I have to be continuous, that's how I know that. Remember, that doesn't switch reversed. Just because you're continuous does not guarantee that you're differentiable. But if you're differentiable, that does guarantee continuity. Okay, where t is measured in minutes and the temperature h of t is measured in degrees Celsius, which they tried to be over emphasizing that because it's in the stem of the problem and they wrote it in the table. So if it helps to think about it as an ordered pair, t comma h of t are the ordered pairs I'm given. This is in minutes and this is in degrees Celsius. If that helps too, then I would label your ordered pairs in general. Values of h of t at selected times are shown in the table above, and now we're finally ready for part A. Okay, part A. Use the data in the table to approximate the rate. Okay, if it says to estimate a rate, approximate a rate, aren't you thinking about the average rate of change, or AROC? So isn't AROC the formula f of b minus f of a all over b minus a? It's really just finding the slope of the secant line, right? Finding the slope. Y sub 2 minus y sub 1 over x of 2 minus x of 1. This is just the upper scale notation for that. So we want to approximate the rate at which the temperature of the tea is changing at time t equals 3.5. And it does say, show the computations that lead to your answer. And we have talked to you guys about this before, but it's been a while because it's doing an AROC problem, and that was more first semester. So if I want to use the data in the table because I don't have a rule to find the derivative at 3.5, that's really what we're trying to do. We're finding the instantaneous rate of change. We're finding h prime at 3.5. But we don't have a rule to find h prime of t in general because we don't have a rule for h of t. And then we can't plug in a number if we can't find the rule. Then what we're really thinking, and we don't have a formula to try and just do math 8 either, is that we're using an approximation. So if 3.5, you want to straddle the numbers that are closest to that, would be between 2 and 5, then those are going to be the values that I want to use into my AROC formula. So I want to use 2 comma 60 and 5 comma 52 into my AROC formula. Now I'm not going to write f of something and f of something because this is the information on h. So I would write, it's going to be h of 5 minus h of 2 all over, in the same order, 5 minus 2. You have to represent a difference quotient. So that show your computation thing means you must show that you're subtracting and you're dividing. Or it would also be okay if you went to straight using 52, because that's what the value is for h of 5, minus 60. And even if you thought, well, I'm going to just real quick say that that's 3, that's fine. Either one of those are acceptable or both of them if you have them both. But you have to show a difference quotient to give you your answer. I would actually stop right here because it's all numbers. But it is calculator active, so then if you type it into your calculator in Pretty Print, you're going to get negative 2.667, or if you left it as negative 8/3, that's the same thing. And remember that we're approximating a derivative, so if this is going to be our degrees Celsius over our time, wouldn't this be degrees Celsius per minute? I don't think they ask you for units, but more as we get into these concept context problems, the more you do with units, the stronger you're going to become, which you're going to need to be strong on that for this year, we have a feeling. So I would try and slap the units on there and like make yourself think about the units on each problem if you have some units going on the original problem. Okay, so there's part A. Part B. Moving on, says, this is a ABCD, so this is a long one. Using correct units, so now they are specifically asking us for units, explain the meaning of 1 over 10 times the definite integral from 0 to 10 of h of t dt in the context of this problem. So we got to explain that first. Then it says use a trapezoidal sum with 4 subintervals, 4 trapezoids, indicated by the table to estimate this. So just real quick talking about the trapezoid part before we explain the meaning of that. Because if you think about, okay, I need to make 4 trapezoids, wouldn't that be from here to here, that would be 1, from here to here, that would be 2, from here to here, that would be 3, from here to here, that would be 4. But those are not equal intervals. So you can't use the trapezoid trick, like the shortcut way. You actually have to run the area of the trapezoid for each one. Because between 0 and 2, and remember in this case, those trapezoids, the change of x would be the height, would be a height of 2. In between 2 and 5 would be a height of 3. In between 5 and 9 would be a height of 4. And in between 9 and 10 would only be a height of 1. So if they are not equal, you can't use that little shortcut trapezoid approximation. You have to do each one separately. Okay, but we'll get to that in a minute. Let's go back to the meaning of this. So earlier, in a different problem this week, we talked about a thing called the function's average value. And it was 1 over b minus a, something multiplied out in front, times a definite integral from a to b of some rule. Doesn't that kind of have the flow? 1 over b minus a, 10 minus 0 would just be 10, times the definite integral from 0, the a, to b, 10, upper boundary, lower boundary, of some rule. Oh, so isn't this really fave of this function? So remember, h of t is our temperature in degrees Celsius of like our tea in our pot that's cooling. So I would say something like, okay, this means the average value, I would use those words, right? This is fave, or the function's average value, of the temperature of the tea in the pot so I'm like going back with the context of the problem. So it's the average value of the temperature of the tea in the pot in degrees Celsius over the closed interval from 0 to 10 minutes. Or you could say for the first 10 minutes. I think that there's going to be more than one way to say it. If you didn't say the average value and you said it's the average temperature of the tea in the pot, that's fine. But you have to have somewhere the average part. You're going to have degrees Celsius, because those are the units of h of t. And remember when we run fave, it's these same units as whatever you're running it on. And you have to have the time frame. Whether you say for the first 10 minutes or over 0 to 10 minutes in words, or from time t equals 0 to time t equals 10 minutes, or in interval notation and then put the units on the end, whatever there, but you have to restate the time at the end. Mr. Herney, can you think of anything else for that part?
No, that sounded great.
Okay. All right, so now going to the trapezoid part, right? Okay, so now we actually, because we can't run fave, because we don't have a rule for h of t, we're going to show what fave would be approximately by using some sort of Riemann sum. So we're approximating this using a Riemann sum, right? So they could ask you to do LRAM, they could ask you to do RRAM, they could ask you to do MRAM. All of those are things that they would ask, especially when you have data in a table, or they could ask you to do trapezoids. Since we didn't have equal intervals, we can't shortcut anything, whether it were rectangles or trapezoids, we're gonna have to run it. So don't lose your 1/10 part. That's just chilling out in front for a while. We're gonna multiply that 1/10 out in front, right? So for my first trapezoid, I would have, and when I think about area of a trapezoid, Mr. Herney had on one that he did, his basis first and his height second. I think about it the other way. So I think, oh, it's 1/2 the height. Oh, the height is the change of the x. My first trapezoid has a change of 2 times the sum of my parallel bases. You guys, the bases, these would be vertical trapezoids like it was on card calculus, are your y values. 66 plus 60. Plus the next one, 1/2 times the height because the heights were different, we couldn't use any kind of shortcut and pull the 1/2 and the height out in front. My height is a 3 on the next one, and my parallel basis would be 60 plus 52. Plus the next one, 1/2 times the height, which was 4, the 52 plus 44 for the y outputs, and the last trapezoid, remember we were doing 4 subintervals, so 4 trapezoids, 1/2 times 1 times the parallel basis, which would be 44 plus 43. And then I'm going to close my bracket to show that all of the 1/10 would be multiplied to that accumulation, that like sum and a product. You're like adding some things that you're multiplying together, which is what they look for on any kind of Riemann sum, whether it's rectangles or trapezoids. And that value would be our good approximation for the function's average value. Okay, I would stop there. Even though it's calculator active, if you mess up then and you say the answer wrong because you typed something in wrong on your calculator, you would lose the points. I think Mr. Herney might have just ran it, just in case some of you did.
I got 50.95.
Ooh, I don't know. That's what it is.
No?
That is supposed to be 52.95.
Oh, that's why you just leave it like that.
That's why you just leave it like that. I think, unless I copied it down wrong from the rubric, which I could have. But I think. I'm going to go over the points real quick on this problem for at least A and B before we move on to C and D, because I might end up needing to erase and needing more space. So on part A, you guys, you just get 1 point. So you had to have your answer, but you had to make sure to get your answer, you showed a difference quotient. If you just had an answer called a bald answer with no difference quotient, you would not get the point for part A. Part B, you had 1 point for the meaning, all written out in words. This is a pretty hard point to earn because you had to say something about the average, you had to have the degrees Celsius so they understood that you knew Faith had the same units as what you're running it on, and then you had to have the time frame. So that one would be pretty hard to earn that point on. It's a hard point in calculus to earn. You got 1 point for showing your trapezoid sum. So not with the 1/10 in front, just with all of this stuff that you're showing that. And then you got 1 point for the estimate, which means did you remember the 1/10 in front? So even if you left it here, it would be fine as long as you had your 1/10 in front. Did you retry it?
It is 52.95.
Okay, so it does end up if you run at 52.95 at the end. So that just stops after 2 digits, so you didn't have to have 3. Okay, but I would have just left it, even though it's on calculator active, like I say, it doesn't really matter. So we have used 1, 2, 3, only 4 points. So this one was a part C and part D, so we have 5 points left to play with. But I just wanted to go through those points in case I ran out of space. Good so far?
Yep.
Alright, so part C. Part C says to evaluate the definite integral from 0 to 10 of h prime of t dt, and then using correct units, explain the meaning of the expression in the context of this problem. So, I don't know. I think this is probably the hardest part of the whole problem, because a lot of you are going to be like, okay, I need to do a definite integral from 0 to 10 of h prime of t dt. If I had the graph of h prime, I would accumulate the area under the curve. If I had the rule for h prime, I would do the actual integral by hand or math9 it on calculator active from 0 to 10. But I don't have anything about h prime. So I think a lot of you are going to be like, I'm out, I don't know how to do this one. And honestly, if you were like that and you skipped part C and you went to part D, but you did all the other parts, that's okay. I mean, sometimes there's going to be a part that you don't know how to do, and don't think just because you can't do C that you can't do D. It should be that you can enter any part of a problem at any time. But think back, you guys, to fundamental theorem of calculus. If I have h prime of t dt and I want to accumulate the area under the curve of it, right, wouldn't it take me back to just h evaluated at the upper boundary? This is the evaluation part of fundamental theorem of calculus, like capital F of b minus capital F of a, but in our case, if this is h prime and we're running the integral on h prime, wouldn't we go back to h at the lower boundary? Oh my gosh, I have stuff about h. This is the table about h. So h of 10 is equal to 43. That's why we can evaluate this. Minus h of 0 is equal to 66. Maybe this is a part where it's nice to have the calculator because we're gonna have to explain what this means, so we actually want to know what the final answer is. So I think this ends up being negative 23. So in context to this problem, right, doesn't this mean, oh, h of 10 and h of 0, h is about the degrees Celsius of the pot of tea, it's a negative answer. Oh, remember that the pot of tea was cooling. Oh, okay, so we've cooled 23 degrees Celsius, or the temperature has dropped 23 degrees Celsius from time 0 to 10 minutes. We just need to say that in words. So therefore, the pot of tea has cooled 23 degrees Celsius from time t equals 0 to t equals 10 minutes. Or maybe you do your closed brackets and write it in interval notation and say minutes. Or maybe you say over the first 10 minutes. All of those are fine as long as you're restating the time. If you don't restate the time, you're not going to get that explanation. Okay? So while we're on that part C is 2 points. So if you, like I said, skip that part, it's 2 points. It's okay. Did you get the value? And did you get the meaning? Okay, and there would be lots of okay ways to explain the meaning as long as you had the degrees Celsius part and you said something about cooling or the temperature dropping and you say the time frame. So part D. Woo, on part D, at least it's a little bit algebra-y. So if you're like me, an algebra lover, maybe part D is your favorite part. At time 0, biscuits, ooh, right? Tea and biscuits, sounds like we're in England. With temperature 100 degrees Celsius were removed from an oven. The temperature of the biscuits at time t is modeled by a differentiable function b. That also implies that b is continuous. And we know b prime, not the original b, but b prime of t is equal to negative 13.84 times e to the negative 0.173 t power. Using the given model, at time t equals 10, how much cooler are the biscuits than the tea? The teapot tea. Right? Not T the letter. Oh, okay. So I have this rule, b prime of t. Remember, it's calculator active. If I want to know how much cooler the biscuits are than the tea, this is the rate of change, right? B prime. And it's showing you in prime notation. So this is going to be the degrees Celsius per minute. If I just want to know the degrees Celsius for the biscuits so I can compare it with the tea, then don't I want to integrate? And it's calculator active. So aren't we going to store that in our calculator in Y1? And after we store that in our calculator in Y1, then it's going to be easy to set up on our home screen. So if I want to know at time 10, this is a little tricky. This is, in my world, what I call that twist on the fundamental theorem of calculus. So I want to know what my actual degrees in Celsius would be at time 10. Well, at time 10, don't I have to take where I start at time 0, although they gave you that, and add it to the definite integral from 0 to 10 of b prime of t dt. So that's what I call that twist on fundamental theorem of calculus. If you want to know a final value, don't you take your initial condition and add it. Remember, this time or this x has to match this time or this x. Wherever you're stopping is where you're stopping, right? This is going to accumulate your degrees, but then you got to know where you start. So do you guys remember reading in that problem when I was reading out loud that it said the biscuits started at 100 degrees Celsius? So this would be 100 plus, and then you would just go ahead and bring this down and math 9 that. So Mr. Herney, did you do that on the calculator for me?
I did not.
Oh, look at that. Someone's slacking on their job. Aren't we surprised? I ended up getting, when I did this on my calculator, and then Herney can show you in a minute, 34.183. So this would be my degrees Celsius at time 10. For the biscuits, they're probably using B for biscuits. Okay? And remember that you had to have that initial condition. So if you just did some integration there, that would just give you the degrees Celsius from time 0 to time 10, but you didn't start at 0 degrees Celsius for the biscuits. They came out of the oven and they were 100 degrees Celsius. Okay, well remember we're really trying to compare it. Okay, now I think he has it. So this is what your calculator screen should look like when you type that part in. he did his plus 100 at the end. I would have done it at the beginning. It's okay because the calculator would like have you finish out the dx notation there. So that 34.183, okay? But now remember that we're not just finding that answer, we're trying to compare it to something. We're trying to say how much cooler the biscuits are than the tea at time 10. So remember that our tea, we have information for. We have our degrees Celsius at times 10 for the tea. So H of 10, just reading it right off the chart, was that at time 10, we had 43 degrees Celsius for our tea. So then wouldn't we just want to subtract these to see the difference between them? So I'm being really bad, but I'm going to just go in this little spot. So we want to do H of 10 minus B of 10. We're going to subtract that again on our calculator. I think you get 8 point something, 8.817. So then I just want to wrap it up. So therefore, the biscuits are approximately 8.817 degrees Celsius cooler than the tea in the pot at time t equals 10 minutes. And again, you want to restate the time because that's probably not what's happening all the time. That's what's happening at that instant of time. Okay, so the last point values for part D, since we've gone through all the other points for the other parts. So on part D, you got 1 point for knowing that you were going to have to integrate from 0 to 10 of b prime of t. So did you know that you had to integrate here? So it does say the integrand. So even if you didn't put 0 to 10, if you knew you had to integrate b prime of t, you would have got that point. That's a pretty soft point, actually, to earn. You got 1 point for using your initial condition. So either one of those steps would have counted. Some of you might go straight to 100 and not write b of 0. So if you knew you had to use your initial condition that the biscuits at time 0 were already 100 degrees Celsius, you got a point. You got a point for your final answer, because I think we only have 3 points left. So then did you make sure that you said something in words and said that you knew, because you compared them, that the biscuits were approximately 8.817 degrees Celsius cooler than the tea at that time. So that one would have been a little hard because you did have to subtract and then you had to explain it in words and you had to restate the time. So that would have been the harder point to earn. So 3 on C, we had 2 on C, 3 on B, so there's the 5, and we already had the other 4 from the other parts. Okay, so if you watched this after you already submitted and turned in that homework, and if you struggled anywhere, maybe on C and D, maybe you got better at that. If you forgot the difference quotient, if you tried to do the shortcut and thought you had equal intervals, you're learning as you go. Good?